So we've used this circuit to show that a resistor is an ohmic conductor. In other words, it obeys Ohm's law. As we increase the potential difference across it, the current strength through it increases by the same factor. The two variables are directly proportional as long as temperature is constant. And this was the data that we found, and it gave us a straight line graph showing that potential difference and current strength are directly proportional for this 2K2 resistor. That's true for all resistors, because resistors are ohmic conductors. Now let's use a similar process to find out whether an LED is also an ohmic conductor, whether it also obeys Ohm's law or not. So we're going to use the same circuit that we used before, except that instead of having the 2K2 resistor in that position, we're going to put an LED in that position. So all we need to do is to remove this 2K2 resistor and put in the LED. But we must make sure that we put the LED the right way around. We can see that this side here of the circuit is connected to the positive terminal of the battery. And so we need to have the long leg of the LED connected there, and then the short leg there, which is then connected to the negative terminal. So I'm simply removing the resistor from the circuit and transferring the connection straight across to the LED. So I take the resistor out there, disconnect it from the variable resistor, put the LED in its place, and there we have our circuit. Let's just check it through. There we have the battery, 9-volt battery. Let's start following its negative terminal. The negative terminal is connected to one side of the variable resistor. Here's the negative terminal connected to one side of the variable resistor there. I'm just going to screw this LED in place just to hold things nicely. It's not necessary, but it just stops things from sliding around. The other side of the variable resistor is connected to the LED, to the negative side of the LED, in other words the short leg of the LED. So remember, we don't use this first leg. The middle leg is connected to the negative terminal, then this last leg is connected straight to the LED, to the short leg of the LED, the one I haven't painted red. I've painted the long leg, the positive terminal, red. So this is the short leg, the negative terminal, and it's connected there to the variable resistor. Then the positive terminal of the LED, the long leg, is connected to the ammeter. Here we can see this is the long leg, the one that I've painted, and it is connected to one of the terminals of the ammeter. So here you can see, here's the ammeter, and the ammeter is going to close the circuit over there because the other side of the ammeter is connected to the positive terminal of the battery. And the only thing that I haven't shown you is the voltmeter connected across the LED. So this one is a voltmeter, and you can see there are its probes, and they are connected there across the LED, not across the variable resistor, across the LED. So this one's a voltmeter, this one's an ammeter, so we must turn this one to the voltage 20 maximum range, and this multimeter we must turn to the current strength maximum 20 milliamperes range, and then we close the circuit. Now, one thing we have to be very careful about in this circuit is that an LED must not have a high voltage across it. So if we were to make this variable resistor all the way over here, so basically a 0 ohm variable resistor, then the full V cells, let's say it's approximately 9 volt, would be across the LED, and that would make the LED very bright. If you do that, you'll see the LED almost glows pink. It's so bright, and it will glow only for a short while, and then it will fuse, and then you'll wonder what's wrong with your circuit, and it's because you've put too high a potential difference across it. So we need to make sure that we don't turn this variable resistor all the way to 0. So we're not going to go all the way to the extreme end there. We're going to maybe start over there. It doesn't matter what our readings are anyway. We must just get 4 readings, 4 voltage readings and their associated current strengths. So we don't have to start with the variable resistor turned right to the end. So for safety, we don't go all the way to the end. We can start in this position over here. And just to be sure, let's just touch it, and we see we're not getting a very high reading there. So we're safe. Maybe even go a little higher. Okay, let's start there. Potential difference of 2,34 volts and the associated current strength 17.2 0.21 milliamperes. We turn this dial a little bit. Now our potential difference is 1,96 volts and the current strength 4,60 milliamperes. Let's move the dial a bit more. And now we have a voltage of 1,86 across the LED and the current strength through the LED 1,70 milliamperes. We take our last reading and we get 1,83 volts across the LED, 1,03 milliamperes through the LED. Switch our meters off to save the batteries. So what do we see here? We do see that as we make the voltage less, the current strength also does become less. Or if you want to put it the other way around, if we look from the bottom up, as we make the voltage more, then the current strength through the LED does also become more. However, even though this is the more, or the less, it's not by the same factor. Well, let's compare the change from the first to the second reading for the voltage and for the current strength. Why don't we multiply 2,34 by to get 1,96? How do we find that out? We simply go 1.96 divided by 2.34, and that gives us 0,834, let's say. In other words, if you say 2,34, you can try this out, multiplied by 0,84, your answer will be 1,96. So we could say increased the voltage so many times, which is a decrease, by the way, because this value is less than 1. Has the current strength changed the same amount? Well, let's check it. If we multiply 17,21 by the 0,84. We have it on the calculator, so let's just say multiply by 17.21. What does it give us? It gives us 14,4, not 4,60. In other words, the factor by which the voltage has been changed is not the same factor by which the current has changed. These two are not proportional to one another, because although the more, or the less, it's not by the same factor. Let's plot a graph of this data that we got. So we're now doing it for the LED, not for the resistor. When the potential difference was 2,34, then the current strength is way up. It's off our graph. I can't even show it. It's up here, 17,21. When the potential difference is 1,96, the current strength was 4,60. When the potential difference was 1,86, then the current strength was 1,0. When the potential difference was 1,83, then the current strength was 1,03. We could have taken more readings, but we know another reading, when the potential difference is 0, the current strength will be 0. We get this strange shape graph. It's rather difficult to draw, something like that. And this shows that current strength and potential difference are not proportional to one another. It's not that they're inversely proportional, they're not proportional at all. What about the resistance of the LED? We know that resistance is equal to the potential difference across the conductor divided by the current strength through the conductor. That gives us the resistance of the conductor. So here we have our data. Let's calculate the resistance of the LED for each situation. Remember, resistance is equal to potential difference across divided by current strength through, and if we use the units volts divided by milliamperes, we get the unit in kilo ohms. Okay, that's what we're going to do. 2.34 divided by 17.21, 0,14 kilo ohms. Next set of data, 1.96 divided by 4.60, that's equal to 0,43 kilo ohms. 1.86 divided by 1.70, and that gives us 1,1 kilo ohms. Finally, 1.83 divided by 1.03 gives us 1,78 kiloohms. So what can we see here? The resistance of an LED is not constant. It changes as the potential difference across it changes. So Ohm's law is not true for an LED. It's true for a 2K2 resistor or any kind of resistor, yes, but not for an LED, because the potential difference is not directly proportional to the current for the LED. If it was, resistance would be constant. That's one characteristic of direct proportion, that when you divide one of the variables by the other, you get a constant value. We've also seen that although the less, it's not by the same factor. These two are not directly proportional to one another. So Ohm's law does not apply for an LED. So it shouldn't really be called a law, because a law is meant to apply under all known circumstances. But anyway, it does not apply for an LED and some other components too. So we call an LED a non-ohmic conductor because Ohm's law does not apply to it.